Okay, this is day 7, so it's just a review of the probability rules, which means I'm just going to give you a little overview of what is going on. So on the first page, these are all the general rules that you need to know. If it says the probability of A or B, that's the union. So you're adding them together and then subtracting anything in the overlap. The probability of A and B essentially means you're going to be multiplying. So multiply them together if they're independent, right? It's just probability of A times probability of B. On the off chance that they're not independent, all right, then it would be the probability of B given that A has happened. So you just have to change that value, which are the questions where, you without replacement type of deal. Down here, the other rules you need to know: conditional probability, how to calculate the probability of A given B. So it's the probability that both happen divided by whatever the second part is, the fact that you're in that category in the first place, or vice versa. Mm-hmm. And then test for independence. You want to check and see, is the probability of A given B the same as the probability of just A all by itself? If it is, then B had no impact on A at all. Right? Those are your basic rules. So the examples that are done here, some of these, this one was off of a Regents exam a couple years ago. They can get wordy. Read them once, then read them again. Then maybe lay out like, what the heck are they asking for? So this particular one gives you data about jogging from students with 2 older siblings in the table versus one sibling. So this is saying here whether or not the student jogs, and they say, okay, if you don't jog, you're in this category. If you do jog, you're down here. So you can see there's a lot less kids that jog than kids that do. I don't know. And then here is talking about if they have no siblings that jog, if they have one sibling that jogs, and if they have both. So like the setup is given that they have 2 siblings. All of these kids have 2 siblings. So it's whether or not none of their siblings jog, one of them jogs, or both of them jog. Okay. So it says use the data to determine whether a student with 2 older siblings is more likely to jog if one of them does or if both of them do. So you're just comparing, So the fact that it is a given one, do you jog given that you have one sibling that jogs, or do you jog given that you have 2 siblings that are runners? All right. So to do the first part, you need the totals, and the totals aren't given up here. So I added up, if you have one sibling that jogs, the sum of those 2 comes out to be 2239. I added up, if you have both siblings, it comes out to be 1780, because you're going to need those numbers, right? Now you can see I've got this highlighted in yellow. I've got this part highlighted in red, so you can kind of see where the information is coming from. So when it says, all right, what's the probability you're a jogger given that you have one sibling that jogs? Well, student that jogs, and you have one sibling that jogs. There's your overlap. So 416 out of the total number of kids that have one sibling that jogs. So the total that have one sibling is the 2239. That comes out to be about 0.185, and it keeps going. All right, then you play the same game over here. What's the probability that you're a jogger given that you have 2 siblings that jog? So that means you have to have both. So you're a jogger and your siblings jog. That's the 400 here in the overlap, divided by the number that have 2 siblings that jog. That's that total 1780 right there. That comes out to be about 0.22. So big shocker here. You're more likely to be a runner if both of your siblings are runners, which, kind of makes sense. Maybe you're more exposed to it or whatever else. All right, you're not much more likely, but you're more likely. All right, so that's what the question was asking. All right. The next one, again, read through it. If you need, this is just an overview video, so you can pause any point you want, try the question, and then listen to the explanation. Mm-hmm. So this one is talking about students that are taking AP US History, which I know a bunch of you guys have the APs coming up, so good luck. They're saying students are only allowed to take AP US if they've taken AP World or AP Euro. Okay. So out of the 825 incoming seniors, 165 took AP World, 66 took AP Euro, 33 took both. Based on that, what's the probability if you pick somebody at random that they would be allowed to enroll in US History? So what it's asking you is, have they taken one or the other, or maybe even both? Well, that's what they're asking, because that's what you need to have done to be allowed to enroll in APUS. So, or means you add, but don't forget, you don't want to count the same person twice. So you subtract anybody that was in both categories, right? Because you only want to count that person once. So probability that you were in AP World was 165 out of the 825. 66 kids took Euro out of the 825. 33 took both of those classes, so we subtract them out so that we don't double count them. And there you go. That's what you're left with. Right? As for the very last one, again, it looks wordy. Take your time reading through it. Try to really break it down. So it says the probability that a resident of a housing community opposes spending money for community improvements on plumbing is 0.8. So they're opposing money for plumbing. That's why I wrote oppose plum 0.8. Okay. Probability a resident favors spending money on improving walkways given that the resident opposes spending money on plumbing issues is 0.85. Again, to try to simplify that, probability they're good with the walkways given that they oppose the plumbing, 0.85. All right. Determine the probability that a randomly selected resident opposes spending money on plumbing and keyword favors spending money on walkways. So the probability that they oppose plumbing and they favor the walkways and translates into multiply. Now, in this case, we would typically say just multiply the probability that they oppose plumbing times the probability that they favor the walkway. But think about how they've given it to you. They've given to you, they oppose plumbing, and then times they favor the walkway given that they've opposed plumbing. It just means that they're not independent events, but this is perfect. So it's this one times the walkway given that they oppose plumbing. You're still multiplying those together. So the product comes out to be 0.68. And there you go. That's it. All right. The last page. Here, I like these ones. I would strongly suggest using the two-way table for this one. You can use a Venn diagram, but I think the two-way table is easiest. Okay. So in the chart, let's see, they give you contract negotiations between local government agency and its workers, estimated 50% chance that there's an agreement that will be reached on the salaries. It is estimated that 70% chance that there will be an agreement on the insurance and a 20% chance that no agreement will be reached on either issue. All right, so when I read that, I wrote this down over here. The probability, salaries, 0.5. Probability of insurance, 0.7. And now when I say that, like them making an agreement on salaries, making an agreement on insurance, probability that not either of those happen, 0.2. All right. So in the two-way table, you always want to have the probability that something will happen and it won't happen, so that the salaries will happen and they won't happen. On the side, I did insurance will happen and not insurance, being agreed upon. And then you want the totals. So that's how you set those up. So one category on top, one on the side, totals on the ends. In here, what you can see is the information that they gave me. I put that in the blue. So the fact that they tell you the probability of the salaries is 0.5, that's the total. So that's the 0.5 that went down here. The probability of insurance was 0.7. That's the total insurance. That's the 0.7 here. The probability that neither happens, so no salaries, no insurance, that was the 0.20. That went right here. Let me zoom in just a little bit so you can see that better. All right. And then you have to know that when you're given probability, it always adds to 1. So those 4 circles, or 4, squares, I should say, the 0.5, the 0.7, the 0.2, and the 1, that's enough to kind of backfill the chart. So you know that this row has to add to 1, so that has to be a 0.5. This row has to add to 1, so that needs to be 0.3 to add to the 0.7. And then you can work your way up. 0.3 plus 0.2 gives you the 0.5 here. 0.10 plus 0.2 gives you the 0.3 there, and so on. Okay. And so you can work your way into filling out all the pieces of this. So when it says find the probability that an agreement will be reached on both issues, the probability of both, meaning salaries and insurance, that's that first square. So that's 40% right there. Easy. All right. So once you have the chart, it's really simple to answer that. All right. Part B of this. Part B is saying, based on your answer, determine whether an agreement on salaries and an agreement on insurance are independent events. Okay. So is insurance independent from the salary being agreed upon? So probability that you're going to get the insurance was 0.7. Probability that you would agree on the insurance given that you agreed on the salaries. In that case, the bottom has to be the total number in the salaries column. So I'm going to slide back up. That's what all this circling was. So that's the total of the salaries, 0.5. And then what's the chance you agreed on the insurance? That was the 0.4 out of that 0.5. So it actually is more likely in this case that you'd agree on insurance given that you agreed to the salary piece of it. So if they're not equal, then you'd say they're not independent. So they're tied together, which is not super surprising when you're actually talking about negotiations that, okay, you agree to this only if they give you this as well. All right, last question. Last question is kind of interesting because it's a little open-ended. It tells you they polled 200 kids, and then they said, for this group of students, you've got like kids that are male versus female, and then music styles, and they picked specifically techno, rap, and country. Very aware that those aren't the only music styles, but it's just what's in the chart. So it says, for this group of students, did the data suggest that gender and preferred music styles are independent or not? So it doesn't matter what gender you focus on and what style of music you focus on. You just got to pick something and compare. So what I looked at is I said, all right, what's the probability that you like rap given that you're female? Is that the same as the probability of just liking rap in general? That's one way I can test this, right? So the probability that I like rap, given that I'm a female, means I have to be in the female category. So in the female category, let me slide so you can see this here. I added up the females because there weren't totals given. So anytime you're not given the totals, just get them yourself. So added up, there's 106 females. What's the probability you liked rap given that you're female? Well, there's 25 females out of the 106 that like rap. So that's the probability that you like rap given that you're female. All right, what's the probability that you like rap out of the whole group? Well, come back up here. The total number of kids that like rap, right, is this 65 right here. 25 females and 40 males. And then what's the probability out of the whole group? 200? Well, 65 out of 200. When you calculate, this comes out to be about 0.23. This one comes out to be about 0.32. They are not the same. What this particular music style, is suggesting is that you're more likely to like rap if you're a guy, which kind of makes sense. There's more guys up here that like it than girls. Okay, so music styles and gender are not independent, or you can say they are dependent.